So I want to give you a rundown of what's called kinetic molecular theory, which we've actually been applying the entire time that we've been talking about gases, because we've been talking about ideal gases. And these things mean that you have gas molecules that are very small. We assume that they're not surrounded by a lot of stuff and they really only bounce off of the container that they're in. In general, sometimes they bounce off of each other. But they're in constant motion and they're going to travel in straight lines, and they only change direction when they hit the container. The next thing we say is that the pressure of the container is a result of gases hitting that container. Next, we say that the average kinetic energy of gases are measured as temperature. Now, this is something we're going to talk a little bit more about here in a minute. And finally, we say that gases do not attract or repulse one another. In other words, the collisions are elastic. Things just bounce off of each other if they do hit each other or the container, and we assume that they do not lose energy. Now, all these things are assumptions, which means that in truth, they don't totally hold up. But we're going to assume they do, just so we can do some math, okay? And talk about things in general, like what they probably would be. So there's two important equations here, because we're going to talk here about kinetic energy. Now remember, kinetic energy is the energy of motion. So as these molecules are moving, we can calculate some things. We can say that Ke is equal to 1/2 of mu, that's a squared up here. Well, kinetic energy is kinetic energy, and that's related to temperature. We'll talk about that in just a second. And then m is mass, and the mu is speed. Okay, so your mass and your speed has to do with how much motion you have. That's some of the foundations of physics, so you've probably seen that before. Next, we say that Ke on average is 3/2 RT. Now, there's a way to derive this, but I just skipped ahead this time. What this means is that there's a constant value that is between kinetic energy and temperature. So we can talk about the average kinetic energy relating to temperature. And what that also means is that it depends on how fast molecules are moving as to what we see as temperature. And that is what temperature sort of is measured as. So there's some cool things here that result. First of all, as your temperature increases, the kinetic energy of the molecules broadens. So in other words, if we have a lower temperature, that means that this is the representative of all the molecules down here, the different speeds and stuff. So it's a narrower range of speeds that they're going to have. But as you increase that temperature, that speed, the variation can start to increase quite a bit. So it does tend to broaden and widen. You can end up having things moving very quickly up here and things moving very slowly down here. A similar effect happens if we keep the temperature the same, but look at the size of the molecules or the mass of the molecules that changes. So in other words, if you have a lighter gas, like here we have argon, you have sort of a narrower range of molecules moving at a given temperature. But as we get into smaller molecules, that's going to broaden because our mass ends up being smaller as well. So smaller molecules, you can have a lot of things moving very quickly or very slowly as well. Okay, one other thing that I wanted to note for you all is we did not totally talk about mole fraction before, and I assume that we've talked about this enough to where you all are probably okay with it. But I just did want to mention that mole fraction is the amount of moles of A over the moles of the total. So if you've got a gas that's like A plus B plus C, the mole fraction of A would just be this. So you just take the moles of A and divide it by the total number of moles. And that's it. Thank you very much.